All right, this is section 1.7, absolute value inequality. So section 1.6 was over absolute value equations. Now we're looking at inequalities. All right, so if you'll remember, when we solved inequalities, the same, everything can still hold. Now, when you solve absolute value inequalities, this is going to be a little bit different. All right, so it's going to be very important um, that you learn or you memorize what the two absolute values are going to do. So the first that we're going to look at is when you have the absolute value is less than k. Now k is greater than 0. Now think about it for a minute. If k is greater than 0, then that means it's a positive number. So when your absolute value is less than a positive number, you're okay. Okay, so when your absolute value of k, when your absolute value is less than k, that's going to be equivalent to this statement. Now notice how it turns into a three-part inequality. Okay, so look at what happens to k, what it equals. So as long as this number is a positive number, you're good. All right. So you're going to set it up this way. All right. So here's what this is going to look like. So the example that they give us is if x is the absolute value of x is less than 3, then it's going to run from -3 to 3. And we can easily test this. If we were to plug -1 in, well, the absolute value of -1 is 1. 1 is less than 3. If I plug in a 1, the absolute value of 1 is 1, so 1 is less than 3. If I plug in a 5, the absolute value of 5 is not less than 3. And if I plug in a -5, well, the absolute value of -5 is 5, which is still not less than 3. Okay, so that's why it turns into an intersection. Okay, so we look at number 1. Here's our absolute value. We still have to consider, is it isolated? Yes, it is. Now, is it set to a positive number? Yes, it is. So we're good. So here's what's going to happen. We're going to take what's inside the absolute value, we drop it. Now we're going to say that it's less than 5 and that it's also greater than -5. So we're just going to put it in the middle to make it a three-part inequality. Now we're going to solve this. So how do I solve this? Well, I subtract 3. I better show my steps on this one. So we're going to subtract 3 everywhere. And then also while I'm doing this, going back to what I mentioned earlier when we solved the three-part inequality, do not split this up. Do not split this apart. Okay, so we have -8 and then 2. And then notice our smaller number, we started out with the smaller number on the left, the larger number on the right. We're still good. So now we're going to divide both sides by 2. Okay, so we get -4 is less than x is less than 1. Okay, so our set notation is the set of all x such that, and then we just rewrite the statement. And our interval notation is going to go from -4 to 1. And since we have strictly a less than, we're going to use the parentheses. Okay. Now, if it helps to draw the picture, here's -4 and here's 1. They both have parentheses and we want everything in the middle. Now we can check it. If I choose, let's say 2, no, sorry. if I choose -1, well, 2 times -1 is -2. -2 plus 3 is 1. The absolute value of 1 is 1, which is less than 5. Now, I cannot choose -4 or 1 because they are not included. They have the parentheses. If I choose 0, 2 times 0 is 0. 0 plus 3 is 3. Absolute value of 3 is 3, which is less than 5. Okay? All right, number 2. We have to isolate. So we're going to have the absolute value of 2x plus 5. I have to get rid of the 2. So I subtract 2, which gives me a 9. Now, my absolute value is isolated. And is it set to a positive number? Yes, it is. Okay, so that means we're going to have -9 is less than or equal to, because that's our inequality. Then we have 2x plus 5 is less than or equal to +9. Again, I'm just following the pattern. Okay, so subtract 5 from both sides. So we get -14. Well, here's the 2x in the middle. And then we have the less than or equal to on both sides. So we get -14, and this is a 4. Smaller numbers on the left, larger numbers on the right. Now, I'm not going to show this step, but I'm going to divide by 2. So we get -7 is less than or equal to x is less than or equal to 2. So here's -7. Here's 2. We have brackets and everything in the middle. So our set notation is the set of all x such that -7 is less than or equal to x is less than or equal to 2. And our interval notation is bracket -7 to 2 with the bracket. Okay, that's how that works. Okay, now that's how you solve when you have a less than inequality. The absolute value less than k. Now, when you have that the absolute value, and I don't know why they changed that. That should be a u, not an x. Let me see if I can fix that. Nope, I'm just making it worse, but it should be the absolute value of u is greater than k. Okay. I think I accidentally did that. All right, so when your absolute value is greater than k, again, k has to be a positive number. It's greater than 0, so it's positive. Then that's going to give you the outer regions, which is going to be the union. Okay, so we can plug this in. In order for this to hold, if I were to choose 5, well, the absolute value of 5 is 5, which is greater than 3. If I choose -5, the absolute value of -5 is 5, which is greater than 3. Okay, all right, so number 3, notice that it is not isolated. Even though it's set to a positive number, I can't guarantee that. I have to isolate my absolute value. So 5 times the absolute value of 2x minus 3 is greater than, now I'm going to add 1, so that's 10. Next is that we're going to divide by 5, which gives us a 2. So now I've isolated my absolute value, and it is set to a positive number. I'm good. That's what I want. Okay, now notice that we're going to have 2 inequalities. Okay, the first one is that we're going to say that u is less than the negative k. So 2x minus 3 is less than -2. And then the other one we take as is without the absolute value. 2x minus 3 is greater than 2. Now we're going to solve this. 2x is less than 1. So x is less than 1/2. And then 2x is greater than 5. So x is greater than 5/2. Okay. And man, I quickly ran out of room. All right. Well, that's okay. So let's put them on a number line and see what this is going to look like. Now, I know what it's going to look like. It's going to look like this, where I have two regions. Okay. So again, make sure that you write in proper, you put them on the number line correctly. So 1/2 is smaller than 5/2. 5/2 is 2.5. Okay. So here's 1/2. And then here's 5/2. So we have that x is less than 1/2, and then x is greater than 5/2. Okay, so here we go. Let me squeeze this in. So my set notation is a set of all x such that, and then I'm going to write these two with the or. Okay, because again, notice that up here you have an or. That's going to be the union. So we're going to have that x is less than 1/2, or x is greater than 5/2. Okay, now my interval notation is going to be negative infinity to 1/2 with parentheses, union, because it's an or, and then we're going to pick up 5/2 and run to infinity. Again, with parentheses, because that was the inequality that we were given. This could have been an equal to, like number 4 is. Okay. All right. Now I want you to try number 4 by yourself, and let's see what you get. So I'm going to pause the video in 3, 2, 1. Okay, this is what you should have gotten. So first we need to get rid of the 1/5. So I'm going to multiply both sides by 5, which is my LCD. Now that I've isolated the absolute value, it is set to a positive number, so I'm good. And so the equal, because it's greater than, or remember, it applies for greater than or equal to. So since it's a greater than, then I drop the absolute value. So 3x minus 3 is less than or equal to negative 15. And then the other equation would be 3x plus 3 is greater than or equal to 15. So I solved each one, and there are my solutions. Then I wrote my answer in set notation as well as interval notation. Okay. All right. Now 5 and 6 are special cases. So let's think about this for a minute. So 5 says the absolute value of 2x plus 1 is greater than 0. Now, my absolute value is isolated, but remember, whatever it's set to has to be a positive number. Since this is set to 0, 0 is neither positive nor negative. But my inequality says that whatever this is, which remember, this, no matter what's inside here, this is always going to come back to be positive, right? So any positive number is always going to be bigger than 0. Okay, so this is always positive or 0. Could be either one. So that means it's the set of all x such that x, I can also write it this way, is an element of the real numbers, any number. And so if that's the case, then that means that I have an infinite solution. Okay, so there's nothing to solve here. Now, if you did try to solve it, you would have 2x plus 1 is less than or equal to negative 0. Well, that's still 0. And then the 2x plus 1 is greater than 0. But if you solve it, you're still going to get the same answer. Okay. Now, this one, again, since this is always positive, it's always positive, and can never be negative. So if this is always positive, then how could a positive number be less than a negative number? And it can't, okay? So that means this is a no solution. And you have two notations for no solution. You can either use that symbol for no solution, or you can use the empty set, either one, okay? But no solution. And then again, I don't remember how Alex is going to want you to enter in your answer. All right, so those are the two special cases. All right, last problem is a word problem. So let's look at this. Now, it says the pH of the water in a public swimming pool should be maintained at a safe swimming value of 7.4. That's the value it should be set at, 7.4. Slight variations in the tested value of the pH levels are accepted, but should differ from the ideal pH balance by no more than 0.2. So if it's going to differ, it can't differ any more than 0.2. Okay, so it says if X represents the exact pH value that's tested, write an absolute value inequality that represents a safe interval. Okay, so here's the first thing. It can differ by no more than 0.2. No more than 0.2 means it has to be less than or equal to 0.2. Now, it can fluctuate. It could be a little bit more than 7.4, or it could be a little bit less than 7.4. So if we just say that X minus 7.4, whatever that is, whatever X is, if I subtract 7.4 from it, it can't differ any more by 0.2. Okay. So I can do that, or I could set this up and say, if I start off with 7.4, whatever the real value is, cannot differ by more than 0.2. So either case is going to work. All right. Now, they want us to solve this. So I'm going to take this one. This is the one that I'm going to solve for no particular reason. So my inequality, it's my absolute value is isolated. It is less than a positive number, so I'm good. So that's going to give me, if it's less than, then that's going to give me the intersection. Now think about this. It can differ. It has to be within 0.2. Okay, so that's why we have the negative and the positive. All right, so we're going to solve this. So I'm going to add 7.4 to both sides. So this becomes 7.2 on that side. This becomes 7.6. Okay, so we just solved it. So the pH may range from 7.2 to 7.6. Now, how do we know we're right? Well, let's check it out. If X is 7.2, 7.2 minus 7.4 is 0.2. Well, negative 0.2, but absolute value would make it positive 0.2, which is less than or equal to 0.2. So we're good. If it's 7.6, 7.6 minus 7.4 is 0.2. Again, that would be positive 7.2, which works. If you plugged it in over here, you're still going to get the same thing. Okay. So that's how that one works. It wasn't too bad. All right, guys. So that's it for 1-7. And I believe that concludes all of your material for chapter 1. So let me know if you have any questions.